Picture this for a second. You've got a stream of water, right? But it's so incredibly pressurized, moving with such blistering speed that it can literally slice straight through solid steel. Or think bigger. It can effortlessly spin a multi-ton power generator at a huge hydroelectric dam. We usually think of water as this soft, gentle liquid, but man, when you crank up the velocity, it acts like an unstoppable solid. So how exactly do engineers actually calculate that raw, destructive, and yet totally productive physical power? Welcome to the Mechanical Engineering Masterclass. I am absolutely thrilled to be your professor today for this explainer on the impact of jets in fluid mechanics. We're going to strip away all that dense, textbook jargon and build a really intuitive, visual understanding of how moving fluids exert massive forces on solid objects. All right, let's dive into this. Here's our syllabus for today. We'll start by unleashing the water jet, then we'll uncover the golden rule, the impulse momentum theorem. From there, we'll test our math on 3 real-world scenarios, striking a vertical wall, deflecting on inclined plates, and harnessing power with curves. And finally, we'll hit the chalkboard to solve some real-world numericals together.
Section 1. Unleashing the water jet. We're looking at the physical path of a high-pressure fluid.
Now, before we touch a single equation today, I want you to visualize the physical reality here. Imagine a high-pressure pipe narrowing down into a nozzle, forcing the water to aggressively accelerate and shoot out as this perfectly formed high-velocity jet. When that jet finally smashes into something, the resulting force depends entirely on what it hits. As engineers, we categorize this into 2 main states. First, a stationary plate. Think of this like the jet hitting a fixed brick wall. The plate just doesn't budge at all. Second, a moving plate. This is exactly what happens inside a real hydroelectric dam, where the jet hits a turbine blade that actually gives way and spins to absorb the energy. For today's explainer, to build our foundational math, we're focusing entirely on those stationary brick walls to figure out exactly how much force that water delivers upon impact.
Moving on to Section 2, the impulse momentum theorem. This is the absolute golden rule of fluid mechanics.
So the crucial point is that every single collision, every splash, every turning of a turbine blade we're going to study today is governed by this one beautiful principle of physics. The impulse momentum theorem states that the force exerted by the jet on a body is directly equal to the rate of change of momentum of the fluid over that body. Let's translate that into plain English, shall we? Force fundamentally comes down to how much the fluid's velocity changes upon impact. It makes sense, right? If you abruptly stop a massive, speeding wall of water, it's going to push back with immense force.
And this concept translates directly into our master formula. Force in a specific direction, let's just call it the x direction, equals m dot, which is simply the mass flow rate of the water multiplied by the initial velocity minus the final velocity. And hey, mass flow rate, that's really just density times the cross-sectional area of the jet times its velocity. So if you remember anything, keep this equation locked in your head. Force equals mass flow rate times the change in speed.
Section 3. Striking a vertical wall, or as I like to call it, the violent, sudden stop. Let's transition to our first physical scenario and put that master formula to the test. Paint a picture in your mind of our perfectly straight water jet slamming directly, perpendicularly into a flat, unyielding vertical steel surface. Now, what's really interesting about this is the sheer violence of the physics at play. Think of it like a car crashing head-on into a brick wall. The water is traveling incredibly fast in the horizontal x direction, but the very split second it hits that flat plate, all of its forward energy is violently stopped and forced to redirect 90 degrees, splashing straight up and straight down. The forward velocity is just completely killed.
So let's walk through the logic step by step here. Step 1. Our initial forward velocity is simply v. Step 2. After the crash, our final forward velocity is 0. It literally has nowhere to go forward. Step 3. Because that final velocity drops to 0, our master equation beautifully simplifies itself. The mass flow rate, which remember is density times area times velocity, just gets multiplied by the initial velocity v. And that leaves us with this clean, elegant formula. Force equals density times area times velocity squared. Notice that velocity is squared. That is absolutely crucial. If you double the speed of the water, you literally quadruple the destructive force.
Section 4. Deflecting on inclined plates. The sideways slide. Now we're going to introduce the next level of complexity. What if the wall isn't flat against the jet, but actually angled? We'll compare this to a race car banking on a steeply sloped turn. It doesn't crash head-on, right? Some of the energy is absorbed into the wall, sure, but a lot of the car's momentum is preserved as it slides along that curved surface. Trace the jet's path with me here. It hits the incline at an angle we call theta and violently splits, Some water shoots up, some shoots down, and because the plate is tilted, the force isn't just pushing straight forward anymore. As engineers, we have to break this force down into two distinct directions, perpendicular to the plate and horizontal to the initial jet.
To translate that slightly intimidating vector calculus into intuitive concepts, let's clearly distinguish the two forces happening. We've got the x-direction component, which I like to call the forward push. This is the force actually trying to knock the plate backward, and it's calculated by taking our base formula and multiplying it by sine squared theta. Then we have the y-direction component, or the sideways slide. This force tries to shove the plate up or down, and we find that using sine theta times cosine theta. Ultimately, the angle dictates the whole shebang. Moving to Section 5, Harnessing Power with Curves. This is the secret to real turbine efficiency.
Real-world machinery almost never uses flat plates. Engineers absolutely must account for curved impacts. Why? Well, because if you fail to calculate the exact graceful angles on a Pelton wheel turbine blade inside a massive power plant, the machinery will literally tear itself apart from the stress. And this brilliantly illustrates why curves are so powerful. Look closely at a center strike. Instead of a violent 90-degree crash, the curved bowl shape gracefully catches the jet, guides it smoothly along the metal, and actually reverses its direction. The water leaves heading backwards. By reversing the velocity instead of just stopping it at zero, you massively increase the rate of change of momentum, which maximizes the physical force transferred directly to the turbine. It's engineering magic.
But of course, we don't always perfectly hit the dead center of the bowl. Often, jets enter tangentially from the side. You can instantly spot the difference when you look at these two scenarios side by side. On one hand, you have a symmetrical tangential impact where the jet enters and exits at the exact same angle, so we just use one angle, theta. But on the other hand, you might have an unsymmetrical setup. The jet enters at a steep angle and exits at a shallow one. This unsymmetrical exit forces us to use two different angles, theta for the inlet and phi for the outlet.
Section 6, Solving Real-World Engineering Numericals. Time for our chalkboard lab session.
All right, welcome to the Chalkboard Lab session. It is time to roll up our sleeves, put our hard hats on, and apply everything we've learned to calculate the actual physical force on a complex, unsymmetrical curved plate. Let's move to the data and see how this builds, pulling numbers straight from a real engineering field problem. We have a jet diameter of 75 millimeters, so about 3 inches thick. We've pre-calculated the area at 0.004417 square meters. The water is absolutely screaming out of the nozzle at a velocity of 30 meters per second. It strikes tangentially at an inlet angle theta of 30 degrees and smoothly glides off the outlet angle phi at 20 degrees.
Okay, let's crunch the geometry and fluid mechanics together. Step 1, we select our specific formula for the horizontal force on an unsymmetrical curve. Fx equals density times area times velocity squared multiplied by the sum of cosine theta and cosine phi. Step 2, we plug in our variables. The density of water is our standard 1,000 kilograms per cubic meter. We multiply that by our area, then by 30 squared for our velocity. Then we take all of that and multiply it by the cosine of 30 degrees plus the cosine of 20 degrees.
And step 3, the big reveal. We run the numbers to find our final mathematical solution, 717.2 newtons. I really want you to take a second and appreciate the immense, real-world physical force that number represents. That is roughly 1,600 pounds of continuous crushing force created by just a 3-inch stream of water sliding across a curved piece of metal. It's an absolutely incredible testament to the hidden power of fluid momentum.
Class, you've done an outstanding job today. We've successfully built a foundational understanding and calculated the massive forces acting on stationary flat walls, inclined slopes, and complex curves. But I want to leave you with this provocative thought as we wrap up. Everything we calculated today assumed the steel plate was locked completely in place. So what happens to our force equations and the sheer power generated when those turbine blades finally give way and start spinning at thousands of RPMs? Well, that is the fascinating world of moving plates, and I cannot wait to explore it with you in our next mechanical engineering masterclass. Until then, keep questioning how the world works.